I would like to start with showing you a little bit or giving you some information where Marburg is located. This is the map of Germany, and you may know that the capital of Germany is Berlin. And another town you may have heard of is Frankfurt. The main airport in Germany is in Frankfurt. And just 100 kilometers north of Frankfurt is my place located, Marburg. So it's in the center of Germany. Marburg is a small town. Marburg has only 80,000 people living there. We have 21,000 students at the moment. So many students compared to people. Our chemistry department has 700 students and 22 professors. You see on the left side that we have a castle on the top of a hill, the Marburg Castle, and that's a view from the air of the chemistry department. So you see the chemistry department is located in a forest area. It's a very nice place. The Mensa is the university restaurant, so it's not far away. This department is now 30 years old, and we will get a new building. And I'll show you a picture of the new building. That's the construction side of the new building. So you see there are trucks around and a lot of dirt, it's rainy. That picture was taken 2 weeks ago. And just half an hour ago, I went to the internet. We have a webcam where you can see every 2 minutes a picture of the construction site. And I will show you now a picture of the construction site of our new chemistry department that was taken 30 minutes ago. It looks like this. First, of course, it's dark. It was 4 o'clock in the morning in Germany. So it's mainly dark. There is some lights, and you see there's lots of snow. So the difference is it's dark, and at the moment there's lots of snow in Germany. So you learned about the chemistry department and that there's a new construction of a building, and that's how a construction site looks like at night. But I'm here to talk about science, and today I will try to cover 3 topics. First topic will be the total synthesis of natural products. The second topic, I will talk about ion channel engineering, and then if we have time left, I will talk about conformational switches. I will also try to discuss some problems with you. And I will now ask a question, and in 30 minutes we will talk about a possible answer. The question is the following. Is this structure large enough so you can read it? Okay. That's a secondary alcohol that can be oxidized using chromic acid, H2CrO4, to get a ketone. You learned about oxidation reactions, so that's a simple oxidation, but that's not the question. This alcohol is a stereoisomer of the first one. It has a different relative configuration. Here the two substituents are cis, and here the two substituents are trans. The trans alcohol can also be oxidized, and the same ketone results. So that's the background of the question. Two stereoisomeric alcohols are oxidized to the same product. The question is, which reaction is faster? The cis case or the trans case? Which is faster? That's the question, and in half an hour we will talk about that. So in the back of your mind you can start to think about this. Which reaction is faster? The cis or the trans case? This is a terse-butyl group, yeah? Terse-butyl. Okay, so that's the question. Now I go to the total synthesis of natural products. Next week I will give another communication, a lecture here, and I will talk about these target structures. So if you are interested in the total synthesis of these compounds, come in next Wednesday. Today I have chosen to talk about annonaceous acetogenins. These are natural products you can find in the fruits of Rollinia mucosa. They have a strong cytotoxicity, and their target is the mitochondrial complex 1. These compounds have a polyether part and two side chains. At the end of one side chain is a butenolide located. Two examples are Rollinia statin or hydroxyazomycin. These natural products have tetrahydrofuran rings, and we and others have synthesized compounds containing tetrahydrofuran rings in the polyether part. There is a subclass of these natural products, and they consist of a tetrahydrofuran ring and a tetrahydropyrane ring. Mucocin is one example, and gymenocin is another example. Many or several groups in the world contributed to that field. I will have to acknowledge them, and we got interested in synthesizing these compounds because of their bioactivity and also because of this rare tetrahydropyrane ring. If you look at the THP rings more closely, you will see that the stereochemistry is the same in mucocin and gymenocin. So let's have a closer look at the THP substructure. You see in red the THP substructure, it's nearly identical. Well, it has the same biosynthesis. So we have a cis disubstituted dihydropyrane ring. Secondary alcohol is the same at C23, and at C20 we have the same stereochemistry. So we asked ourselves the question, how can we synthesize this substructure? And how could we apply this synthetic solution for a total synthesis of mucoxine and gymenocine? Let's ask the question, how could you make this? There are numerous possibilities. One disconnection could be at that position. If you make this bond as the strategic bond, you could have an intramolecular epoxide opening. If you have an epoxide, an alcohol can intramolecular attack the epoxide. This epoxide opening is normally initiated by a protonation to activate the epoxide, and then the alcohol has two possibilities. It can attack here to give a 6-membered ring, or it can attack in this position to give a 5-membered ring. So it's a problem of regioselectivity. Have you learned anything about the normal regioselective attack of an alcohol? If I have a normal alkyl chain here, will it attack to the left or to the right side? What would you guess? What have you learned? It normally attacks here. This is the so-called Baldwin rule. But behind Baldwin rules is stereoelectronic. You need a collinear arrangement of carbon, oxygen, carbon in the transition state. And that is less strained for the 5-membered case than for the 6-membered case. So normally you get the 5-membered ring. Maybe I should draw the 5-membered ring. So normally you get this product, a 5-membered ring. We want this attack to occur. But normally you get the 5-membered ring. In order to get the 6-membered ring, you do an allylic activation. If you have a double bond here, this is an allylic position. It's activated for nucleophilic substitution. And then you get the attack to get the 6-membered ring. So it's a regioselectivity problem, and it can be solved by the introduction of the double bond. That's the background of the regioselectivity. So that's one possibility. We could, by an intramolecular epoxide opening, make the THP ring. There's another possibility.